fusion
Yeah.
decays to bottom quarks and machine learning techniques.
Okay,
So after this long title, we expected very
Self-explained,
nice,
right?
But yeah.
Questions?
I think you don't need to.
So you have the pointer, perhaps?
I think
Where is it?
it's here.
Johanny was hiding it from me.
Yes.
On purpose, I know. Okay, so thank you very much to the organizing committee for giving me the opportunity to give this talk. Last year I was giving the talk on the CMS highlights for physics and stuff, and this is going to be a phenomenology talk. Okay, it's a different topic. And I will start saying that this talk is for the students. I really don't care about the professors. So you can be bored as you want. I want to motivate some of the students over there. So just to remind you, so we've seen this Lagrangian many times, and John, did an excellent job, Rain an excellent job trying to explain, what this implies. And I will just add to what is being said already about the standard model. Of course, that is the summary of our understanding of elementary particles and their interactions, right? But upon everything that they said about this nice Lagrangian, I will add that this is it's a model that is based on the tensor product of three different gauge groups, okay? And we know, thanks to Amy Netter, a nice mathematician that told us that for every single symmetry there is, so we should have a conserved quantity, right? So each of these symmetry groups is attached with a generator that basically becomes a gauge boson, and that's how we explain particle interactions. Of course, it's been excellent, very great at explaining many things, but it has a lot of conundrums and open questions that still we haven't been able to answer. And that's why we're here, right? Just trying to see what are we doing in particle physics to answer some of those questions. Okay, you can think on different models, that people have proposed. Supersymmetry, is one of my favorite. I have searched extensively for supersymmetry at LHC for many years. John, I'm still trying with my team to look for supersymmetry, compressed mass spectra with vector boson fusion, ISR jets. We'll do it, man. So we also have B minus L models, leptoquarks that I also have been working extensively, and for many years. Randall-Sundrum models with Kaluza-Klein excitations, meaning that they give rise to new heavy possible mediators that could explain extra dimensions. And there is a particle that is close to my heart because I did my PhD thesis on this particle that's called the Z prime. And this particle appears in every single one of these extensions, okay? And the simplest thing you can do to extend the standard model Lagrangian is to consider an additional U1 symmetry. And you might be thinking, what is this? It's just a rotation, an additional phase. That's the simplest thing you can do. And then the consequence of this, if you look at your interaction Lagrangian, here is the Z boson. So here is where your photons are going to come. And here you get, once you extend the standard model by this phase rotation, you get the Z prime. And then you work on your, you get your mass Lagrangian, and then essentially, you have this max matrix, and there is some mixing terms between the Z boson of the standard model, which we know, we've measured, and we love the Z boson, and the Z prime, which is a new hypothetical, neutral boson. It could be very massive, it could be light, we don't know. The couplings are also open. We don't know about really the features of the Z prime, but we need to probe everything we can to see if we can find such a particle that could enlighten our understanding, of the standard model, or physics beyond the standard model. So then you have to diagonalize this, mass matrix, as you know, to go to this physical basis, and then you have here, the mass of the Z prime, and in the lambda minus value, you have the mass of the Z prime plus some correction that includes mixing between the Z boson and the Z prime. Another important, observable is the width of this resonance. So we need to be careful with this, because if it's too broad, of course, we start running into problems. And then, so we basically have into consideration the couplings as free parameters, the width of this resonance, we basically try to control to make it, not very broad. And with this very simplified phenomenological approach, we say, okay, if we measure this type of particles, right, experimentally, how do we measure it? right? It could decay to electrons, to muons, to jets, to be quarks, to tops. We don't know. So, and these limits have a lot of tears, blood, and sweat from experimentalists. This very nice plot, I'm proud to say that it was me. You know, I made the plot with other collaborators. And this is a lot of bounds of exclusion that say we haven't seen anything. And essentially we have proved the Z prime considering that it has the same couplings of the Z boson of the standard model, right? It decays to the same rate, you know, as the Z boson to electrons, to the muons, to taus, and that's an assumption. But the universe doesn't have to be like that. The universe is what it is. And there are other models that say, okay, what about if this particle has a strong, strong couplings to third generation fermions, meaning taus, be quarks or tops? It is possible. And there is interesting physics, the anomalies, G-2, right, that could be explained, through this type of scenarios. Then, okay, we say here we haven't seen this, but a lot of these searches, have strong considerations. And this is what we were talking, and Francesco was talking, during his talk. A lot of these models, there is a lot of assumptions that we make. So we need to check these limits carefully, okay? And I had huge arguments with some of my fellow theorists at Universidad de los Andes, who is, I hope they still like me, but I have also a strong opinion because we're not gonna see anything at the LHC, and then, wait a minute, it's not so quick, okay? So, Large Hadron Collider, this is the tool we're using to probe some of this physics. It's the highest energy particle separator ever built. We're colliding currently protons and heavy ions. Is 100 to 150 meters underneath the French-Swiss border. Beautiful machine. We have 7 experiments, 4 very big ones, big experiments, and 3 smaller size experiments. And so we have here at Uniandes, we've been contributing to these CMS experiments. It's compound muon selenoid. I always said it's better referred to as constant mental stress, but we'll see. And then I also worked on Atlas. So I was, also a partner of Gabriela and Johanny on Atlas for a few years. I was a postdoc over there, and we have people from Universidad Nacional also working on LHCb and working on Atlas, and we have now also people in Colombia working on Atlas. So we're trying to put this little contribution to the LHC physics program. But this is not really as an experimental talk, it is a phenomenology talk. So we came up with this idea with some friends where we said, okay, what about if this subprime has these strong couplings, to the third generation, and people have been studying, the production of subprime to the fusion of top quarks. Basically, we have gluon is spinning to top and to top, and then here another gluon is spinning to top and to top, and then they fuse, produces subprime, and people study, the decay of this subprime considered also decay to top quarks, but it has some caveats experimentally. We said, if it couples to the top, it has to couple to the bottom. And what about if we propose this type of search that CMS and Atlas have been performing, but we consider decays to be B bar, right? And it could be like a simple idea, but it has some serious implications in the end, and that's why we got published. So let's explain a few details on the search. So first of all, we basically produced some simulations of signal and background samples using MATGRAPH, and we consider, collisions on the center of mass energy of 13 TeV and 14 TeV, and the Z prime masses and the couplings, are free parameters in this simplified phenomenological approach. And we essentially consider a scenario where the Z prime, for example, could have the same couplings of the Z boson, but we included this G tau tau, which is a modifier that allow us to basically change the level of coupling of the Z prime. Let's say it could be 0.1, 0.2, 3, 0.3, etc. So it's just a very simple idea. That's what we call simplified phenomenological scenario number 1. Then we have another scenario where the Z prime is considered a color single vector particle. And then here you have the interaction Lagrangian, you have here some chiral terms, for right-handed terms, for left-handed chiralities and stuff. So it can be factorized in this way, where this effective coupling is the square root of the sum of the chiral couplings square. And there was some nice experimental work where Atlas and CMS proved that this theta parameter, so tangent theta is equal to CR over CL, basically the ratio of these chiral couplings, that the production cross-section does not depend on theta. So we made an assumption, based upon these nice results, papers that have been published, and we choose, theta equals pi halves, and then we obtain production cross-sections, and we perform the phenomenological analysis that is of interest for experimentalists as well, considering, these assumptions. All right, so how we did the analysis, we start with a Lagrangian. So we basically use what we call here the universal fermion output. So using Fermi rules, mathematical package that allows you, to have this Lehouchez, basically this input that then we can put in MATLAB, right, and produce the same or simulate, the proton-proton collision, produce the cross sections, everything. We can essentially start changing couplings and do many things on the theoretical side. And then, of course, you want to emulate this type of event, with the same conditions at the LHC to see what experimentalists, might measure. So that's why we use this software that is called Pythia to simulate, parton showers and so on and so forth. And then we want to incorporate these interactions between particles and detectors, right? So that's what we do with a software that is called Delphis that allows you to basically smear a little bit the momentum of particles, incorporate reconstruction efficiencies, fake rates, all of these nice and important experimental settings. So once you have that, so we apply some selections to these simulations, and we basically filter a little bit our data, and then we use machine learning techniques to see if we could tell the experimentalists if they perform the analysis this way, how sensitive could be the experimental search to probe this type of production at the LHC that has not been done yet. Okay, that's the paper. Okay, so then for machine learning, so we started like 3 years ago, and then the pandemic hit and stuff. It was a mess. At the time, we were trying to explore this gradient boosting decision tree algorithm. It's not the most up to date, but it was nice. It was what we learned, and then we used a library that was called scikit-learn. So what we did basically was to filter out the data and then train the algorithm. So for those that know machine learning, you have to basically optimize the learning rate, find the best possible set of variables that give you the best performance of the algorithm. You have to optimize the number of layers, many things. And then what this software gives you, right, is a probability of the event for being signal or being background after you train. And it literally gives you an output that you can put in a histogram where you have the probability of an event being signal or background. And then after this, so what we did is to start understanding, once we have filtered the data, which were the most important variables, right, to separate signal from background. And we studied 47 different observables. So we correlated positions, PT, everything you can think of. But we came up with 4 variables that gave us the 90% rejection power of signal to background. They were the most important ones, which basically were the PT of the BJets, the separation of the BJets, and the reconstructed mass of the 2 BJets, the 2 highest PT BJets in the event, which you could have even up to 4. So with these variables, essentially, the algorithm performed quite nicely. And then what we did is to perform a statistical analysis of the output of the results, which I'm going to show you in a minute, using what we call a profile beam likelihood. Okay, essentially, you have this likelihood formula where you have a number of expected background events, a hypothetical signal, and then the question is how likely is that the background will fluctuate, to give you the signal. And once you basically have a background-only hypothesis, essentially, if it's extremely unlikely that the background fluctuates to give you the signal, that's what we call the p-value. If your p-value is really, really, really low, you invert the p-value, and it means that you have a lot of significance to detect your signal, because your signal is so high up, with respect to the background, that it's very unlikely that the background will explain the signal. Then you get your signal significance that way. So these are examples, of the output of the gradient boosting algorithm. So here you have some of the backgrounds. We consider TT bar plus X. X means W, set bosons, TT bar Higgs, and 4, pair of tops. This is the most common type of backgrounds in this type of analysis. This is one of the signal benchmarks. And you will see that here we put a GQ equals 0. That's a scenario where we essentially suppress the couplings of this Z prime to the first and the second generation, and we enhance couplings to third generation. And then GQ equals 1 is where we have a more democratic scenario where the TT bar, so the Z prime can couple to electrons, to muons, and to taus to a degree. Both are interesting, for theoretical studies. So then here you have your signal, and you can see, that signal on average is quite well separated from the background. So we did the profiling likelihood to estimate the significance using the output of these distributions, and then we got, after almost 3 years of work, these significance plots, as function of Z prime masses. And here we put some lines that you can see some numbers, 1.69. It means, with what is level of precision, you can, at 95% confidence level, perhaps, exclude some of these signal models. And 3 sigma and 5 sigma for potential discovery. And then the way how you can, or you must read this plot is, for example, for 5 sigma, if you want to discover, Z prime with these theoretical features for 5 sigma, you can probe, these type of particles up to roughly 700 GeV, and so on and so forth. So we did studies with different luminosity scenarios for the high luminosity LHC, considering, this center of mass energy of 14 TeV for different luminosities, and then we tell the world, with what accuracy we can probe this type of search. What is interesting, and people might be thinking, but there is still like the Z prime to, top anti-top search. Correct. But the thing is that if there is a Z prime with preferential coupling to third generation, it must couple also to be quarks. That's our assumption. And what happens is that the reconstructed mass, of the Z prime to BB bar has much better resolution for reconstruction than the reconstructed mass of Z prime going to top anti-top. Because the top anti-top decays fast, there is missing T, there are so many things, right, that they make the mass really broad and make the rejection power, experimentally, significantly smaller with respect to what you can achieve with the BB bar search. So we basically show that. We show that naturally, because the decay width will go as coupling square times the reconstructed mass of the botton system square over the mass of the Z prime square, that the width of the BB bar, separated to BB bar, is so much narrower that the signal will be very well separated with respect to the background. And then if you perform the analysis with machine learning, you can have a huge improvement and complementary and competitive search with respect to other searches that have been performed at the LHC. So we, of course, also ran, our analysis as function of different set of couplings. We vary the couplings, as function of mass, and we place bounds, considering, the scenario where GQ, the couplings, the suppressed couplings to first and second generation, or the GQ equals 1, where you basically do have couplings to first and second generation. See, these plots are on the left, GQ equals 0, and on the right, for GQ equals 1. And this is essentially shown, for the different luminosity, or 2 different luminosity scenarios for the current run 2 luminosity and our future luminosity in the next 2-3 years at the LHC. We expect to have or gather array like 350 GeV in the next 3 years, hopefully, if we have enough running time. Right now there's a big discussion, and you believe it or not, the war in Ukraine is limiting our ability to run the LHC. There is serious problems with money, energy, and everything. So there is a huge if, things go well, and stuff, so we will be able to achieve this type of luminosity. Okay, so I hope that it convinced you that this search could be novel to be probed at the LHC. And again, just for reference, if you want to look at the paper and cite us, so at some point for your future work, that would be very nice. So thank you very much.